reaction. And this is also a method for making alkenes. So in the end, this particular reaction is also a method for making alkenes. Oh, sorry. Big whiteouts through this. Sorry about this. I'll even put it in a Sharpie here. We're working on E1 reaction today. And this is also a method for making alkenes. Yesterday in class, we were working on E2, which is a very special type of reaction, uses base, good leaving groups. It's a method primarily for making alkenes. And we're going to think of E1 in that same context. We'll be making alkenes with it. SN2 and SN1 were substitution reactions, so we could make all sorts of different products with those. E2 and E1, they only make alkenes. This process will also sometimes be known as a dehydration of alcohol or alcohols to give alkenes. And this, in our class, is going to work with H2SO4. It also works with another acid, H3PO4. But the acid that we're going to spend all our time on this semester, I won't use any H3PO4. We're just going to focus our attention on H2SO4 and alcohols. This will really keep E1 separated from these other three reactions we've been studying. This particular reaction isn't terribly useful synthetically. Making carbocations has some problems with it. You rearrange sometimes, and we don't always get what we want. But treating alcohols with this strong type of acid, this very special acid, sulfuric acid, results in what's called a dehydration reaction, where it means loss of water. And so in general, let's just look at a specific example. Let's take T-butyl alcohol plus H2SO4. This would work with H3PO4. And what we get out of this reaction, in the end, is an alkene plus water. So this will be the general reaction that we're always seeing. It should be a little bit familiar to it. I hope you did okay on the quiz type problems we had with this today. They might have been a little challenging. I'll take a look at them later and see how you did. But this type of process is new. It's an elimination reaction. It's called E1. It's unimolecular. And the rate of this reaction is a function of a rate constant times the concentration of the substrate. Whenever we had this 1 after a reaction, it was always just the concentration of the substrate. Whenever we had 2, yesterday it was substrate and base. When we had SN2, it was substrate and nucleophile. But the speed of this reaction is really only dependent on how much of this we have. This gives us a clue that it's a carbocation type reaction. Let's work through this step by step. You saw it already in the preview lecture, but let's actually go through this step by step. And it's actually going to give us a chance, too, to revisit acid-base chemistry, reinforce some things. It's the way I've developed our lecture for us today. Let's take T-butyl alcohol. Go through all the possible steps that could happen. And we're going to write sulfuric acid out in Lewis structure, or one of them. And we're just going to think about how these two things react with one another. Well, sulfuric acid should already give you some clue that it's an acid. Okay? From all the reactions we've seen, we know something about this, that this is a horrible leaving group on its own. So this molecule does nothing on its own. It's not going to leave on its own. It'll make hydroxide. That'd be impossible, especially in a solution full of acid. Instead, an acid-base reaction happens here, which is quite straightforward. And this is an equilibrium process. And we end up with a protonated alcohol. So we would just call this a protonated alcohol. And we have sulfate nearby. I guess I'll draw this down here. A little bit out of space, but it's okay. And this particular species we know is an oxonium ion. That's what we call it. It's very acidic. And oxygen wants electrons. Right? So this species here is called oxonium ion. It's an electronegative atom. Now it's plus charged, really wants electrons, and it also makes these protons very, very acidic in this particular charge state. So one thing that could happen to solve this problem is we could have the reverse reaction happen. This conjugate base here could pick up this particular proton, give these electrons back, and we'd be back to here and oxygen would be happy again. That actually happens, and that's why acid-base reactions are equilibrium reactions. They go backwards and forwards. So one way to stabilize oxygen is actually do the reverse reaction. We could take the base, pull off the proton, give electrons back, oxygen's happy again. So that's one thing we could do to stabilize this oxonium ion. The reverse reaction can always happen. So maybe under here we could always say reverse reaction possible. It actually happens. Just means this base reacts with this acid, we go back to here. So that's one thing that's possible. Let's look at a second possibility. So first possibility, reverse reaction. Let's redraw our oxonium ion. So oxygen still wants electrons. How are we going to stabilize oxygen? Well, if we pull off this proton, give it electrons, oxygen's happy again. But we're just back to where we started. The other possibility is that we take these electrons, not the electrons in the acidic hydrogens, but these electrons, and we just push them to oxygen. And oxygen gets these electrons, gets happy. We can look at our leaving group momentarily and evaluate if it's a good leaving group. And we have water. So this is also very easy to understand. Now oxygen's happy. We've made this very, very reactive species. This carbocation now desperately wants electrons. One thing that could happen to it is it could just simply recombine, and then it goes back to where we were, and then carbon's happy again, oxygen's unhappy. We could pull out this proton, we could go all the way back to the alcohol. So this whole series of sequences and events we're visiting here is really one big, large equilibrium process, forward and backwards, due to all these different reactive species. So this would stabilize this, but alternatively, this carbocation is sp2 hybridized. What I've done here is I've expanded one of the beta positions. Okay, so let's call these alpha and beta again. And this carbon really wants electrons. Right? So carbon in this case wants electrons. We could give them electrons with water. We could be going backwards. The energetically favorable process, however, is that these protons are now acidic as well. Yesterday, when we had a leaving group here, bromine, we found that these protons are acidic. But they're also acidic again, because if we could pull off just hydrogen and leave behind its 2 electrons, then we could give a double bond here and stabilize this carbocation and get a neutral molecule. So these protons at the beta position next to a carbocation are now acidic. That means we could pull off a proton. There's a lot of plus charge here, because this bond's weakening because it really wants to go this way. It's getting pulled this way. And what actually pulls this off, I think the text in the slides I was giving show water, but you could either use water to do this, or you could actually use sulfate, that conjugate base that we had from the last slide. You can use either one of these. They're both basic enough to do this. And the mechanism has similarity to SN1, and now is the similarity to E2, where the beta position's protons are acidic. We can pull one off with a base. Either one of these molecules will work. And the electrons fall between carbon and carbon, and we end up making an alkene from this process. This is a very, very different process than E2 reaction. E2 had strong base, good leaving group. All the E1 problems I'll ask you about that we're going to focus on are going to have a horrible leaving group, OH, that has to be protonated to turn into a good leaving group. The other major differences here is that the E1 reaction is stepwise. The E2 reaction was concerted. All steps happen at once, but the E1 reaction is stepwise. First, water leaves. This makes a carbocation, and then second, elimination takes place. We lose an acidic proton, form a double bond. So these are stepwise processes. They don't happen at the same time. So the E1 reaction is stepwise. First, water leaves. Then we have a carbocation, and elimination takes place where we lose an acidic proton, and we form a double bond. So these are different, and this is the kind of the SN1 version of elimination, where we have carbocation, and then elimination takes place. We already know that the stability trend for carbocations is important. This would determine which of these forms easily. So this carbocation trend we know is tertiary, secondary, primary. Actually, methyl is impossible to form methyl carbocation. So we've seen this trend over and over and over again. So tertiary substrates give tertiary carbocations. They'll be most reactive because the tertiary carbocation is most stable. Secondary works. Primary is very difficult to form primary carbocation. And we know all the reasons why this works. We've seen it with radicals very, very early on in our time together this summer. And we've seen this trend pop up over and over again, especially with SN1, with strong acid additions to alkenes.